Sorry. I'm recording this session, and I hope everyone is fine with the recording. It will be uploaded online for public access. So if you have any concern, please let me know. Otherwise, I'm assuming that everyone is fine with recording this lecture and sharing online. As I said, we have been trying so far to organize our mind to understand that what's going on, how our cognition, our brain, as an intelligent creature, or even simpler creatures, how they interact, what does it mean to work in an environment. We define different type of environments. Environment can be predictable, unpredictable, observable, partly observable, completely unobservable, can be discrete, can be, different categorization we've seen. Apart from environment, which is a very important part of this AI concept, we define a creature inside the environment, or creature interacting with the environment. We call it agent. That agent, gets or perceives information from environment, makes decisions, and applies decisions to the environment. This continuous interaction between creature, or that agent, and environment will define our whole process. For us, we don't have control on environment. We do have control, and we program our agent. And this agent, we hope to be successful. And we define what does it mean to be successful. What does it mean to have a better performance? And what kind of agent we can design. This agent can be, the simplest thing was a tabular form. We define the answer for every question, which we realize that might not be a good solution in many cases, in realistic cases. Then we thought probably it might be a good choice if we make it reflexive, inspired from nature, from what we do as an intelligent agent ourselves. Reflexive means instead of keeping history of what happened, from the beginning, we just try to reply based on what we see. Our agent replies based on current perception. Then we also realized that it has weaknesses. So what to do? We added to this model. We added, the other components to make it model-based, and we made it goal-based, and then we also added learning factor to it. We were trying to grow concept of agent gradually from very, very simple to what is more complex or more intelligent somehow. Now we are going we are taking one further step. So far, I have a general conceptual structure of an agent. Okay, I know that this agent needs to find answers to questions, needs to find solutions for problems. The big question is how. We didn't say anything. We didn't think about that part. Now it's time to think about this part. Our agents start finding answer to questions. Okay, we want to talk about that, and today will be just discussion on search as a conceptual action, not just search generally. We define what does it mean and how we're going to use this search concept in the AI, or in our agents action. Back to my panel. Okay, search. Today I'm going to, at first part, I'm going to talk about search. Why search? What we do in the search, problem types, and defining the formulation of our problem. And actually, at first part, I'm trying to say, well, we know what is search, but how you're gonna connect this concept of search to that agent? You know, for example, the agent, vacuum cleaner agent from last week. Where is search? It doesn't need to search, you know, it's just a simple action. We try to connect this together, and we try to define a problem for those agents, which is a search problem now, okay? And then we talk about search algorithm. I start from a very fundamental concept of tree search, okay? Search strategies. And then on the second part, we start about talking about more detailed search strategies and uninformed search algorithms. Okay, the simplest agent which we've seen here in this course were reflex agents, which base their action as a direct mapping from a state of actions. Such agent cannot operate well in an environment for which this mapping would be too large to store and would take too long to learn. Okay, a reflex agent. In the goal-based, however, as we had again last week, on the other hand, considers future decisions and desirability of their outcomes. See, in the goal-based, in more in smarter agents, we make decision when we make a decision like action one, agent tries to to think about action 2, action 3, and so on. Actually, or from the action ones, but from state as well creates a state of itself or of environment from one state to another state. So, for example, I at the moment I am in the vacuum cleaner. The agent is in square A, and both squares are dirty. So this is one state. It takes an action, and this action changed the state. So for new state, it needs to make another decision and another action, and that action changed the states, and so on and so forth. It continues. Okay, so in this sort of agents, we have to think about future actions in terms of sequence of states, sequence of operations or actions we have. What's going to happen next? What's going to happen next? We have to search for the best sequence to get us to the goal, or in state which we consider as our target. We have to go through a certain number of different actions, states to get there. This chapter describes the kind of goal-based agent called problem-solving agent. So we are going to focus on problem-solving agent now, okay? But to do that, we have to define first what is a problem and what do you mean by solving, okay? We have to focus on those parts, and we break those down to basic concepts and then try to write a code or try to build something, an algorithm to run that. Problem-solving agent use atomic representation. If you remember last week again, at the end of section, I introduced you that representation of this agent states can be 3 different: atomic, vector-based, and also inside each state you have more information and more detailed. In this level, I'm considering a basic abstract form of the state. So inside each state, I don't have too many information. It's just one state, and it's atomic form from last week discussion. If you need to, you can refer to see what does it mean according to our discussion. Discussion of problem solving being with precise definition of problem and solution. We have to make that clear. What does it mean? And well, actually, by looking into and discussing on this, we learn more about problem, and we learn more about agents as well. There are several general purpose search algorithms that can be used to solve these problems. Uninformed search algorithms, two important classes of algorithms, are algorithms that are given no information about the problem other than its definition. You'll see that, okay? It sounds kind of vague. What do you mean? But what kind of other information? We'll see that. So uninformed means you have the problem and that's it. No one else is helping you, okay? Some of these algorithms can solve any solvable problem. None of them can do so efficiently. So uninformed search is good and you can find the answer for me, but it's not efficient. Why are we learning uninformed? Because they're based for others. We need to learn first one to be able to understand the second one. An informed search algorithm, on the other hand, can do quite well given some guidance on where to look for solutions. You see the difference now. That's what we do, right? Consider yourself. If you have, if you lose your key, okay? If you lose something, well, you need to search for it, right? That's very basic. You need to search and find it. Uninformed search means, well, I lost my key at home, let's say. I have to find it. Just, you need to search everywhere, even places you've never been, or it's impossible you to go. So that's uninformed search. Since you have a problem definition is I have a goal, a key, and it's lost in a house. Go and find it. But if you have informed search, you get some extra information. I lost my key, but with this information, for instance, you have been there, I have done that, I never go there, I normally go here, last time I saw it was here, you know, you add those information to your search, it makes your search much more efficient, much faster compared these two together. But basics of search are same. When you're searching informed, you're still doing the same thing, same search algorithm, but this time it's guided. You have some guidance. Therefore, we need to look into uninformed search first. But before getting there, I have to talk about problem and solution, concepts of problem and solution. Any questions so far? Very good. Imagine an agent in the city of Arad in Romania. Okay, this is an example coming from book. I don't know why author picked Romania, why author picked this setup. I don't know even if it's realistic. Has anyone here been in Romania before? Do we have anyone who is familiar with Romania, more or less? Never been. Okay. Anyone? No one. Okay, so I don't know if we can confirm that these information are realistic or not from people who have been there. So it doesn't matter. This is a example, and well, it's a beautiful example. I like it. So and encourage me to go to Romania actually. So the age Romanians starting a touring travel. Okay, so we have an agent. We imagine we have an agent in this country, and it can move from city to city, from one location to another location. The agent performance measure contains many factors, and the decision problem is a complex one involving many trade-offs. Yeah, troubling. Suppose that agent has a non-refundable ticket to fly out of Bucharest, okay? The following day. So our agent is in this city, and next day is supposed to be in Bucharest, okay? In that case, it makes sense for the agent to adopt the goal of getting to Bucharest. Okay, so we are defining a problem, we are defining a question. Course of action that don't reach to Bucharest on time can be rejected without further consideration. And the agent's decision problem is greatly simplified if we can figure that out. Goals help organize the behavior and by limiting the objectives that the agent is trying to achieve, enhanced action need to be considered. So let's have a look at the map, okay? I'll come back. So I have an agent. Agent is here right now. By tomorrow, it needs to be here. So a sequence of actions now makes sense. So if my agent goes to here, then here, then here, then here, then here, then here, then here, will be a different sequence of action rather than going here, going here, going here, or going here, going here, going here. It's different ways moving around this map, okay? So our problem is more or less this, okay? Goals helps to minimum this objects. For example, for instance, you might say, I never get here. So I can put them out of my map, of my actions. Or I don't want to go certain ways, and I put them out of my map. But still, your agent needs to make sequence of decisions. Sequence of decisions, okay? Goal formulation based on the current situation and the agent's performance measure is the first step in problem solving. When I want to have a problem, first of all, I have to have a goal. I have to formulate my goal. If you don't have any goal, you can't even think about a problem, think about solving a problem and designing an agent for. If you cannot formulate, for example, a difficult formulation. If you tell me I need an agent to behave very well, I don't know what do you mean by behave very well. If you tell me I need an agent which can be an artist, it's a very vague goal definition. I don't know what do you really expect this agent to do. But if you be more specific, if you tell me that I want an agent which can mimic, I don't know, Michelangelo's work, can mimic Kogan's work, one specific artist and one specific task, or if you narrow it down, then it will be possible to think about the problem. So the first step is you have to have a clear and definable goal which you can formulate. The agent's task is to find how to act now and in the future so that it reaches to the goal. So we are trying to define, right? These are small baby steps to define the problem. I have to think of how my agent needs to do right now, the next step, and also in future in the consequencing steps to get to the goal state. Before it can do this, it needs to decide what sort of actions and states it should consider. Okay, then we have to think about more details. What does it mean actions? Okay, and what are states? We have to define those as well. What are states? What are actions? I'm trying to formulate a problem, how to define a problem. There's a very famous say, well, it says, understanding the problem is half of the solution. Well, in math, I used to say that to students in math class. If you understand the problem properly, you are halfway to solve it. So here we are trying to understand the problem. If it were to consider action at the level of move the left foot forward an inch or turn the steering wheel 1 degree left. See, these are decisions. One agent output can be this, right? Can be just move leg 1 inch forward or 1 degree left. These are too detailed actions. So with these actions, you probably won't be able to get anywhere, okay? So the agent would probably never find its way out of parking lot, let alone the Bucharest, okay? Bucharest away, it can't even move out because these are too detailed actions. Because at the level of detail, there is too much uncertainty in the world, and there would be too many steps in a solution. That's what I'm talking about. You, even when you have your goal state, I want to be in Bucharest by tomorrow, you still need to define what kind of actions and what are states. If you define too detailed actions and states, not good. If you define too large actions and states, also won't be good. So you have to choose right one. So problem formulation is the process of deciding what actions and what states to consider given a goal. So we have a goal, then we have to define what are actions and what are states. What can take us to the goal, basically. So in the problem, first step is define the goal, then tell me what is the way to reach to the goal, or how can I get to the goal. Then I go for finding the solution, okay? Our agent has now adopted the goal of driving to Bucharest and is considering where to go from this city. All right, okay. 3 roads lead out of Arad, one to Sibiu, the other one to Timisoara, the other one to Zenit. Names on the map. None of these achieves the goal. So unless the agent is familiar with the geography of Romania, it will not know which road to follow. Yeah, it's right. It says, if you're at this city, the first choice, assuming that we define states properly. Now we define states as city, right? I would say I am at this city, so my state is, all right. If I go to this city, my state will be Zönyik. If I go to this city, my state will be this city or this city, okay? So we defined our state. States are locations, these cities, okay? My actions would be moving from one city to another city. This is one action, this is another action, okay? So if we define this, our agent, at first, we call this initial state. Initial state, okay, my action at initial state will be 3. This way, or this way. And unfortunately, none of them is the target, which is here. Okay. The agent will not know which of the possible is the best unless it has a map, it has an information, it has sort of connection, information about connection of these nodes together. If the agent has no additional information, then it has no choice but to try one of the actions at random. Yeah, if your agent doesn't have any map, any information about it, you just have to move randomly till by chance it get to the final destination. Suppose the agent has a map. So, because while talking about random movement wouldn't be very efficient right now, I want to assume that there is a map, okay? There is a map. The point of a map is to provide the agent with information about the state it might get itself into and the actions it can take. The agent can use this information to consider subsequent stages of a hypothetical journey via each of three towns, trying to find a journey that eventually gets to Bucharest. In general, an agent with several immediate options of unknown value can decide what to do by first examining future actions that eventually lead to the state of the known value. Okay, so let me go back here in the map and what happened? Where's the map? Not again. It can be something wrong with the. Sorry about that. Don't know why it stopped. Can everyone see the slide again? All right. Thank you. Thank you very much. Okay, just to test ourselves. Let's assume you want to make the decision. Which path or which sequence of states do you suggest to take to get from here to here? What is your suggestion? And tell me, how did you find it, right? We are trying to mimic the sequence of the decision, right? We're Silvio Fagaras. So one pathway suggested is this. And Nasir Khan mentions also this, which we are assuming are distances, okay? Why didn't you take this one? It wasn't shorter. But 80 plus 97 plus 101. Still more, right? Still more or less? See, this one might be shorter, okay? No, I didn't say any condition right now. And actually, this is a good question because you're starting asking about the problem itself. Is the problem complete? If I wouldn't say anything, right? If I wouldn't say anything, I said, we are here at this, and what should be the next move? You don't know what to answer, but depends what do you want to do. Okay, where do you want to go? If I tell you I want to be here, then you give me some answers, but still you might have questions as well. You say, well, are you looking for a way with the minimum cities on way, or are you looking for somewhere with shortest distance? Or do you want to go through certain cities, or don't you want to go through certain cities? Those questions come in, and actually those questions make your problem defined, and you have to include that for your agent through the search, okay? But asking about the sequence, what happened in your brain? How did you do it? How did you find the pathway? What kind of, what was happening in your brain when you were doing this? Think about that. What did you do? Since we have a bird eye here, so we see the map, what we do, we examine all possible paths, not all possible, those which look feasible, all right? Virtually looking at what seems to be the faster, yes. But how do we do that? How do we do that? Actually, we traverse. We We travel, we mimic, we virtually go through it. So, well, I add up this together to here to see how much. And then I do this one, 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 and so on. And I check all paths. I'm not doing that really, but what we have learned with our brain is when we look at that, at parallel, we can do the calculation and actually have numbers for all those pathways and make our decision based on that. Otherwise, if you haven't done that unconsciously, means your answer probably is wrong, because how do you know this is the shortest? You know this is the shortest, right? How do you know it's shortest? Because you compared it, because you found a way to compare. I agree that probably something is happening that you're doing it very fast. You don't even feel it. You just look at it and say, oh, this one is shortest. Okay? Because our brain is trained. Our brain is an agent, have learned these over years. But for an infant or for someone who haven't done that ever in their life, it will be a difficult task. For someone never ever done anything, someone who doesn't make any sense of these locations, distances, movement, geographical shapes, they have to do the calculation. The only way for a person like that is find all possible ways, expand this, and then add them up, and then compare them together, and then pick the one which has the shortest number, or sorry, the smallest number or shortest pathway. Okay, that's how you do it, and that's how you have to build it in your agent. Okay, let's see what's next, what we should do. Okay, sorry, what's here? So suppose agent has a map. If agent doesn't have a map, so I just covered the map. You don't know. You just at every stage. Sorry, I have to go back again. I'm sorry. But, if at each stage you can see only exits from the city, so you don't see anything but this, and this. So let's say for by luck, by chance, you pick this one and you come to this city. You don't have map, right? You see one goes out this way, one goes out this way. So you randomly have to pick one of them. You have no idea where you're going. So it depends on how lucky you are. Where do you go? You might go this way, and then you have one choice and you will be back to where you were. Or you might choose this one, or you might choose the other one, go on path number 1 or number 2 or number 3 randomly. At each one you again have others. So let's say if you pick one, you will be here. Here you again have 2 choices. And it depends on how, this is random. We can do calculation. I can do that. You can do that as well. To tell me if it's gives the same chance to every pathway. So we have no extra information. Completely uninformed. We don't know what is the direction. We don't know. We don't have a compass, anything. We don't know where is the city. We're just randomly walking around. So we can do some simple calculation based on probabilities. At here, probability of picking up each one is 1/3. Probability of picking this one is 1/3. Probability of this one is 1/2. We can build up a probability diagram and say, okay, by the chance of this much X, you will get in Bucharest after n number of actions. We can build that up. In future we might do that for some other approaches, to say if you go for 100% random choices after n action with the chance of X, you get there. For instance, after one move, the chance you be in Bucharest is 0. Because no way, there is no way you can get in Bucharest by one move, one action. With one action, chance is 0. With 2 action, chance is still 0. With 3 actions, 1, 2, 3, you have a chance. We can calculate that. I can calculate that, right? We can sit down and say, all right, if this one is 1/3, if this one is 1/2, yep, it's 1/6. After 2 actions, you get there, because the chance picking one is 1/3, picking this one is the half, and this one is 1. So after 1/6, the probability is this. It doesn't mean that you definitely will be there, but the probability is here. And if I want to define and relate this with time and distance, probabilistically I can build up an equation and say, okay, by the probability of this, after this time, after this kilometer of driving, you get there. Or by, from the other hand, you can say, if you want to be in Bucharest tomorrow by confidence of this much, what is the chance? We can do those calculations, but we put them aside for now. We do consider we have a map. The reason I discuss this is, that if we don't have a map, it doesn't mean that we are hopeless. We still can do something. Many agents are, might be able to do that. If you're sending an agent down deep to the ocean, we do have those sort of agents, okay, robots, okay. Down deep to the ocean, you might not have any map at all. You might not have anything at all. You might have unpredictable situation, okay? But still, you might be able to do something. Any question? No question. Very good. Okay. So I'm changing my problem by giving a map to the agent. If I give a map to the agent, then the map, agent can use the map to serve. Still not an easy job. Still, we have a lot to do because, again, as I said, you have to compare this agent with an infant, with a kid, with someone who has logic capability but never ever seen a map in their life, never ever done any search or travel in their life. They can calculate, they do understand things, but they have to figure it out for the first time. The agent can see this information to consider subsequent stages of hypothetical journey via each of these 3 towns, trying to find a journey that eventually gets to Bucharest. In general, an agent with several immediate options of unknown value can decide what to do by first examining the future actions that eventually lead to the state of known value. Okay, let's have a look at our problem. What is our problem? If I have a map with these assumptions, my environment becomes observable, referring to last week's lecture, if you remember. Observable means the agent always knows the current state. Because it has a map, at the moment, I know that I'm at the city Akrat, so, and I have the map, so my environment is observable, okay? The environment is discrete with our definition. Again, I'm defining that my agent is either in city A or in city B. We don't have anything continuous in between, okay? It might sound like oversimplification, but it should work. It should work for this example. So at any stage, there are only finitely many actions to choose from that. So if you're at one city, you have only 2 or 3 or 1 option to get out of that city to another one. The environment is known. So the agent knows which states are reached by each action. So it can clearly predict state of the environment based on actions. Sorry. I apologize. I'm losing my voice. The environment is deterministic. So each action has exactly 1 outcome. That means deterministic. That you do something, you do that, at the same state, you do the same action, you always get the same output. We call that deterministic. Indeterministic, sorry. Indeterministic is an environment in which at the same step, at the same state, you do the same action, but you might get a different answer. It's not deterministic. There are some kind of uncertainty in the system, in the environment. Under these assumptions, the solution, now I'm defining the solution, okay? Now I'm trying to define the solution to any problem is a fixed sequence of action. So if I ask you what is the solution, then you say these actions is the solution. Go to here, to here, to here, like what you did here. See, I see your answers. Jason said, Arad, Sibiu, Rimio, Pete, Bucharest. Or Nasser Khan said, similar or different. Gino said simply, this is the solution. That's what you did. So you, although we haven't defined it, but you know that by nature, you know that by experience, you know that because you have learned this. Or I would say we are trying to mimic something like what you do. Actually, we're trying to build the agent to think like us. The process of looking for a sequence of actions that reach the goal is called search. Now I understand what does it mean. Okay, I understand what does it mean to do a search. A search algorithm takes a problem as input and returns a solution, the form of an action sequence. It becomes more clear now. Okay, so in that case, a search algorithm is like a machine that you give the problem and you get the solution. Okay, this is a search. And what is a problem? As I defined before, just a few slides ago, a problem is, states and actions defines states and actions altogether, and solution is a specific set of sequence of actions which takes us to the goal. That would be search, searching among all possible sequences of the actions to find the right one. Once the solution is found, the actions in the recommends can be carried out, and we call that execution phase. Well, when you have the solution, then you have to do it. You have to execute that. So thus, you have a simple formulate, define your problem, your goal, then search to get the solution, and then execute. So our agent has to do that. That's what we do as well, okay? When I show you a map, first thing you do is a formulation. You know, this is a map. You already have learned that. What does it mean, a map? But when I give you a new problem, first step is you have to formulate that. You have to figure out what is this, what is the input, what is the output, what are you looking for, what is the goal, and all those details. When you did that, then you search for the answer. You go through those definitions, trying to find out what sequence of actions will take me to the solution, then you execute that. After formulating the goal and a problem to solve, the agent calls a search procedure, which can be a software, to solve it. It then uses the solution to guide to the action, doing whatever the solution recommends as the next thing to do, and then removing that step from the sequence. When it's going through steps which it's done, well, can be removed from the next steps. And when you reach the goal, you might define a new goal based on type of agent and actions you define. Okay, so make it clear. A problem can be defined formally by 5 components. So it can be a kind of exercise or a question in the exam or in assignments. I ask you to define the problem. tell me what is the problem, AI problem here I want to solve. When you try to define a problem, you have to give me 5 items. Item 1, initial state. Where do you start from? 2, possible actions. What are possible actions? Transient model. I'll explain transient model. Transient model means how do you move from one to another one state to other state, or how action moves you from one state to another state. Transient, transition model. Goal test. How are you gonna test that you're at the goal or not? Where and what is the destination, and how do you figure that destination is reached or not? You have to have a clearly defined goal and tell me how can you test that's the goal or not. And path, cost, function. This is also something we need. I didn't talk about that. Well, roughly we did. We mentioned that. In the map problem, with the distance on each map, you can define a cost. You can say, all right, so the cost of going from this city to other city will be this much in terms of distance, or this much of fuel in terms of fuel, or this much of time in terms of time. Okay, so 5 items to define a problem. I'll talk about them briefly just to make sure it's clear. Initial state that the agent starts in. For example, the initial state for our agent in Romania might be, in Arad, a function, a program that says we are in Arad. Okay. A description of the possible actions. What are possible actions available to the agent? Given a particular state S, actions returned, well, if you define a sub-function, a subroutine, it returns the set of actions that can be executed in state S. Okay, possible actions. This is the second item of our problem. For example, from the state in Arad, if I know that I'm in that state, the possible or applicable actions are go to this, or go to this, or go to this city. These are possible actions. If I have that, means I have a well-defined problem. The description of what each action does, the formal name for this is transition model. Okay, the definition of what each action does. What would happen if I take this action? Specified by the function result. So if I'm at this city and I take this action, means I'm gonna be at this city. As simple as that. Well, this is a simple example, but if you think about a more complex type of environment and agents, that would be something to think of deeply. That returns the state results. We also use the successors to refer to any state reachable from the given state by a single action. For example, when we have what is the result, we are here and we go here, result will be we're here. If you're at this city and you take this action, you will be here. Any questions so far? So you see, super easy. What I'm trying to do, I'm breaking down the problem into smallest pieces as much as I can, just to make everything clear and everything simple. For those who want to program an agent, it's very close to writing a program for a simple agent. Together with initial state, so I have initial state, with actions, I know what type of actions, and transition model, if I have the 3, where am I, what kind of actions I can take, and what each action does for me. In that case, I have my state space. State space. State space means kind of a conceptual map of actions inside my agent. If my agent has that many actions it can take, so connection between these and states which I move from one to the other one will be my state space of the problem. Okay, state space of the problem. Each problem has a state space, a normal problem. So you have states and actions. How from one state you go to another state by taking certain type of actions. The set of all states reachable from the initial state by any sequence of actions. The state space forms a directed network or graph. Oh, yeah, it says or graph. I said or graph just by feeling. Yeah. Directed network or graph. This is a mathematical concept. Okay, you can search it online. So directed graph. What does it mean, directed graph? In which the nodes are states and the links between nodes are the actions, similar to what we had before for the map. So we can define our problem as a network. Directed network means nodes and links connecting them together. That will be a state space that can represent a state space. The map of Romania, so for example, can interpret it as a state space graph if we view each road as standing for two driving action, one in each direction. So directed graph has a simple structure of you can go only one way on each link. If it's two-way, means you have another way to go back. So two separate roads to go from A to B on each node. For state space, we consider this. A path in that state space is a sequence of states connected by a sequence of actions. So if I have my map something like this, each sequence of states will be one path from one point to another. The other item of the problem is the goal test, which determines whether a given state is a goal state or not. Sometimes there is an explicit set of possible goal states, and the test simply checks whether the given state is one of them or not. Agent's goal in Romania is the singleton set of in Bucharest or not. So that is the goal. In some other cases might be slightly different. Sometimes the goal is specified not in explicitly, but in abstract, probably rather than explicitly enumerated set of states. For example, in chess, the goal is to reach a state called checkmate. Okay, checkmate. So this is not a specific move or any specific location or any space. This is more conceptually, where the component king is under attack and cannot escape. So sometimes our goal might be more complicated. That's why we need to define the goal and we need to give a way to give a routine how to check whether we are at the goal or not. And the last one is the path cost function that assigns a numeric cost to each path. How can you make difference between different paths? The problem-solving agent chooses a cost function that reflects its own performance measure. So our agent should be able to examine different paths, ways, and different actual costs for them. Here we assume that the cost of a path can be described as sum of costs of individual actions along the path. It's a simple model. So for example, if you are going in state space, going from one location to other one, cost from each one added together will give you the total cost. So if you have cost 1, cost 2, cost 3, total cost will be cost 1 plus cost 2 plus cost 3. And you might come back and say it's not necessarily the same. These costs might be combined non-linearly. So For instance, if you're coming up to here, your total cost will be C1 plus C2. But if you reach to here, your cost will drop increasingly. So it wouldn't be linear. We don't consider those cases. Those also can be included, but we try to keep our discussion at the basic level. Any questions so far? All right, very good. So I did try to define the problem, to understand the problem. Now we need to look to the solution. A solution to a problem is defined, as I said, as an action sequence that leads from the initial state to the goal state. So solution is defined based on action sequence which take you from initial state to the goal state. Solution quality is measured by path cost function. So cost function gives me quality of the solution. And an optimal solution has the lowest path cost among all solutions, okay? So you see the relationship. All components we defined before are related together. I want a solution. Solution is defined on a problem. And in a problem, right sequence of actions which takes us from initial state to the final state will be a solution. Quality of solution is based on the cost function, and best solution is the one with the lowest cost. This information seems reasonable, but it is still a model, still on paper, an abstract and mathematical description, and not the real thing. Still, we don't have that. The process of removing detail from the representation is called abstraction. So this is still in abstract level. Defining the problem, defining the solution, state space, and everything still in discussion level. We haven't done anything in more detail. So now I'm trying to get into more details, talking about research, okay? The abstract is valid if we expand any abstract solution in a solution. So these are referring to abstraction. So it's useful. And what I'm trying to say here is what we have done so far is valid and useful. Now we need to go into more details. Example problems. Let's have a look at problems. Learn more about problems, then move to search. Problem and solution, and then to search. So problems in the context of AI, when people talk about problems and talking about examples, two types of problems. One called toy problems, which are mostly simplified abstract problems, which are good for classrooms, for research, for testing ideas. These are more simplified form. They are toy problems. The other one are real world problems with those solutions people actually care about. And such a problem tend not to have a single agreed upon description. And many of them are more complex. Well, in terms of application, yes, we have to do something here. If I want to sell, if I want to be in the market, I have to work on this. But at university, at classroom, at learning level, at the beginning, we have to focus on toy problems to learn more. So please don't be surprised if in this class we are introducing super simple problems as toy problems, as I mentioned here, just to learn the concepts. First problem, a toy problem, the vacuum cleaner as we had before. I want to see what is the problem. I want to see how can I define the problem of vacuum cleaner as we had there. So if you remember, to define the problem of vacuum cleaner, I have to give 5 items. I have to give 5 items. What are states? What is the initial state? What are the actions? What is the transition model? And transition model, what is the goal test? Here is missing. Goal test, and what is the path cost? Okay. So let's briefly look at that. Since we are familiar with this, let's see what we have. States. The states is determined by both the agent location in that problem. If you remember, just a reminder for myself. The problem was we had two tiles, tile A, tile B, and a vacuum cleaner which could move from this one to right or left, and there was some dirt in the environment. So state is whether the agent is in square A or square B, and whether square A is dirty or not, or square B is dirty or not. Okay, so and the dirt location. So total state space, the agent is one of the two locations, each of which might have might or might not contain dirt. Thus, the total state space is we have two locations and we have combination of 4, like clean, 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 dirty, dirty, clean, dirty, dirty. It will be 4, right? We have two locations, each one binary at two states, either 0 or 1. So we'll be having dirt or not on each square, which gives me 4 different cases, and my agent can be in one of two locations. In total, I have 8 possible world states. A larger environment with n locations, with n tiles, okay, will have n to the power of n times 2 to the power of n states. For example, if I have if I have a 4 tile world, in that case n equal to 4, how many different states I have? What is the size of my state space if n is equal to 4? What would be number of possible states in the world if I have my vacuum cleaner problem instead of 2 tiles with 4 tiles? What would be the size? It would be 4 times 2 to the 4. 4 times 2 to the 4. N, can you see here? N times 2 to the n. Okay, it will be 16 times 4, which is 64 different states, 64 different possible states in my world with only 4 tiles. Okay, so remember that. Initial state. Any state can be designated as an initial state. Means, well, any combination of these 8 possible combinations can be my initial state. I don't have any limitations on that. Action. In this simple environment, each state just has 3 actions. At each state, we can have only 3 actions. Either agent should go to left, or agent should go to right, or agent should suck the dirt. Larger environment might also include up and down. So in this case, in my 4 tile example, my actions will be left, right, up, down, and suck the dirt or clean the dirt. So in that case, I have 4 actions. Okay. Transition model, the actions have their expected effect. Each that moving left in the leftmost square, moving right in the rightmost square, and sucking in the clean square has no effect. So we can define clearly what would be effect or consequences of each action, depending on the situation we have. The goal test check whether all the squares are clean or not. Path cost, for cost, we can define different ways of cost. So each step costs 1, we can define that, saying, okay, moving from one step to other step costs 1. So the path cost is the number of steps in the path. That's one cost function we can define. We can define different kind of cost functions for this problem. So I can define it as this. This environment is completely observable. If it's observable, in that case, two cases, for example, I can assume that the environment is observable or not. Okay, if it's observable, these are 8 different cases. You have dirt, 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 clean, clean, dirt, clean, clean, and same thing here, but your agent is in the left or in the right square. We have 8 possible states, okay? If it's observable, means our agent knows where it is and knows what is the situation of being clean or dirty, okay? So if it's at this state, it knows that it's currently at left is clean, and right is dirty. So the action is, sequence of actions would be move right, then suck. That would be the solution. That would be the sequence of actions which lets us to get to the goal. Okay, that sequence of actions will take us to the goal if it's observable. Okay, but what if it's not observable? So if it's not if environment is not unobservable, if it's at 5, our agent doesn't know where it is. Is it in A or B square? If A is clean or not, if B is clean or not. So in that case, the solution will be, what would be the solution? Okay, you give me the solution. Can you give me the solution? If your agent is at 5 and the environment is completely unobservable, what would be the sequence of what would be the solution, which is sequence of actions which makes the environment clean? Sock, right, sock. Any other? Okay. Here, similar to what you had. It can be sock, right, sock, or right sock, left sock. You know, because it says assuming you start on any of these, that always will be the solution. Always will be the solution. Okay. Jason's suggestion is correct if you are at 5, but if we don't know where we are, that might not work. If we don't know where we are, because it sucks if, let's say, it's here at 6. Jason's solution, does it work? Sorry, not here. Here at 2. If you are at 2, does Jason's solution work? No, because it says sucks means clean. Right means stay here. We can't go, and suck again, and it's clean, and there will be some dirt here. You don't want it. So if you want to have a general solution, you don't know where you are, you don't know what state you are. I made an assumption. I said we are at state 5. That's why Jason's solution is 100% correct. But if I add another extra limitation, say I don't even know where am I, what is the state right now, so the solution will be just right sock, left sock. Check this to see if it's correct or not. Does it work for everyone? So if it's here, it says right means stay here, sock means clean up, then left and sock clean, so it cleans it. How about this one? It says right clean, and sock, clean. Then left and sock, clean. So cleanse it. I have a question here. Could you swap left or right, and would it be the same? This one. So instead of we say left sock, right sock. What do you think? Is it another solution? Does it work as well? Right? Yeah, it works. Again, you have this. We can redo this, and I suggest that you do it for this, for Foursquare, to see what would be the sequence of movements for our agent if our agent is well, the cleaner, and if observable or if it's not observable. It's unobservable, completely blinded in terms of what state we are in. We don't know anything about the state we are in. In that case, what would be the solution? It's right, left, up, down, and sock. What would be the sequence solution for a Foursquare? Think about that. Okay. Sorry, before, yeah, it's good to have a look at this as well. It is a state space of our two-square vacuum cleaner, the toy example. In the in here, well, if you are at this state, if you go left, you will be at the same state. You are not going anywhere. If you go right, you go to this state. You see, if you take action right, you go to this state. At this state, if you take action left, you will be back to this state. At this state, if you take action right, you stay at same state. And you see transition between states. At this state, if you take action S, you will be at this state. So left will be clean. At this state, if you go left, you stay on this state. If you you will be at the same state. So you clean the dirt, you stay at the same state. If you go right, you go to this state. From this state, if you clean, you will be to this state. If you go right, you will be on itself. If you go left, you go to the other one. So this map clearly shows the state space of the two-square vacuum cleaner agent. Two-square vacuum cleaner agent. Okay. So let's go for a short break. And during this, please think about that and give me the solution for unobservable with this. All right. LDUR D for 4 squares, not the most efficient way, Nikita says. Michael says LUS left, down, up. Nikita, you're not using S, not using cleaning at all. It doesn't well, it doesn't make sense in terms of this AI thing. You have to use cleaning S at each one. Okay, so think about that again. Yeah, think about that again. And Michael says left, up, S, R, S. Why left at the beginning, Michael? Why do you have that left? What is the use of just, you don't know where it is, you don't know where it is, so you're saying just go left and go up. Left, up. Okay, you're thinking robotic, right? Okay, left, because at either way you want to set up a location like that. Good. So are you doing robotic programming, Michael? Is it your sort of job? So that's why. Okay, good. So, well, others as well. Think about solutions. So what Michael suggests, he says just left up to make sure that in any case you will be here. Then from here he starts clean this, go right, clean this, go right, clean this, go down, clean this, go left, clean this, go up. And with how many sequences of how many options? L, U, S, R, S, D, S, L, S, 4 for 4 squares. Well done. That's a very good. That was a good solution. Others also can give me other solutions as well. Okay. So we will be back in 10 minutes. I want to give you a short break. I would love to continue, but well, I think will be too many speaking. So see you in 10 minutes, please. Okay, we'll be back. All right, so I stop recording.